Huge congratulations to all the Axis team. It's such amazing news. And I feel honored to be giving the first talk within 24 hours of the acceptance. That's great news. So I'll talk to you today about the field of accretion onto white dwarfs, but particularly focused on the accretion of planetary debris. I'm going to spend the first half of the talk explaining what evolved planetary systems are and what we do and don't know about them. And then the second half will focus on the role that X-rays can play in answering some of the unknowns. Okay. Here's some of the collaborators that have contributed heavily to this work. I'm just going to start with this. This is an HR diagram. On the main sequence there, you see every main sequence star in NASA's exoplanet archive that hosts at least one exoplanet. You see some giant stars also with exoplanets. The white dwarf cooling sequence here is populated only with white dwarfs that show evidence of planetary material in their atmosphere. And this evidence comes from absorption lines associated with metals that we can unequivocally tie to the accretion of planetary debris. So this sums up the evolution from the exoplanets that are intact around their main sequence stars to their ultimate demise once their star evolves into a white dwarf. White dwarfs, once they move off the main sequence, end up losing about half of their mass, and the mass that's left will gravitationally contract into something that's very dense. With surface gravities about 100,000 times that on Earth. This large surface gravity leads to very rapid elemental sedimentation. And within a few mega years, white dwarfs reach loosely reach a structure that looks a bit like an onion, with a carbon-oxygen core, a helium shell on top of that, and a hydrogen shell on top of that. And the photosphere is contained right at the edge of that hydrogen layer. So spectroscopy of a white dwarf should really just reveal Balmer line hydrogen absorption. But that model was already disproved before we even really knew what white dwarfs were. This spectroscopic plate here was taken in 1917. It was taken of it was thought that this may be an F or a K star. But in hindsight, it was realized that actually this was a white dwarf that showed heavy absorption lines associated with calcium, magnesium, and iron. You're seeing at the bottom a much more recent spectrum of the same star. So we now know that this actually is a metal-polluted white dwarf. And the origin of these metals, so the calcium, iron, magnesium should all sink way below the photosphere on very short timescales. So the presence of them in the atmosphere tells you that this has been accreted after the formation of the white dwarf. And the well-established model now is that this accretion comes from disrupted planetesimals around white dwarfs. We'll come to that. So really, this was the very first evidence of exoplanetary material, and that was taken in 1917. Since then, there have been the detection of 23 unique photospheric metals in the atmospheres of white dwarfs, including those that are necessary for rock formation and for the formation of life as we know it. And I love this implied exponential increase, because it's only, makes me ask the question, what are we going to find in the next few years? I think we'll find a lot. Thanks to the Gaia revolution, we now have a catalog of 360,000 white dwarf candidates, with the aid of large-scale spectroscopic surveys like SDSS, Foremost, DESI, and WEAVE. The number that have been spectroscopically confirmed is rising rapidly. We're probably at 50,000 now, and that number is growing. I think DESI is releasing 50,000 white dwarf spectra at the end of this year. And when you go to space, if you look at HST samples, we find that 25 to 50% of white dwarfs show metal pollution in their atmosphere. And this metal pollution is coming from the accretion of planetary debris. And this is roughly in line with the about 1/3 of stars which seem to play host to an exoplanet. So how do you actually pollute a white dwarf with planetary debris? At the end of the stellar evolution, yeah, I see a question from Margarita, I think. Do you have a question, Margarita?
These are all proven to be single white dwarfs, not in symbiotics or interacting binaries.
Yeah, we're here just talking about isolated single white dwarfs. Yeah. Thank you. Good question. So yeah, in the case of just a single star evolution, the previous, the orbital configuration, which reached some kind of stable state, is now disrupted because the gravitational potential has maybe it's halved. The star has lost half of its mass, and so the orbits have expanded in response to this mass loss. And now you have a new dynamical configuration, which can lead to gravitational perturbations of asteroids, comets, moons, small planets themselves. And if you can perturb something onto an eccentric enough orbit, then you have a chance that this could reach the Roche radius of the white dwarf. The white dwarf has a radius of about 1% of the sun, and its Roche radius is about a solar radius. So you have 100 times the white dwarf radius in which to catch planetary objects. And if an orbit is eccentric enough and it reaches this Roche radius, then we expect tidal disruption of whatever the planetary body was. And we see lots of evidence of these tidal disruption events in the form of mostly characterized in the infrared, although not exclusively. So here in the lower panel, you're seeing an infrared spectrum of G29-38. You can see here silicate feature at 10 micron, which is very common in these disks. And James Webb is opening up a whole new line of inquiry with these systems. And we see in the top here, we see double peaked optical emission lines. This is the calcium triplet. This double peak is coming from emission at Doppler shifted emission at either side of the disk. And at the top left, you're seeing a transit. This is a light curve of the first white dwarf discovered to have transiting debris. And there's now a sample of maybe 15 white dwarfs that show transiting of planetary debris, and you can see that the eclipse light curve here is very, very chaotic, and we see variations actually in the transit over the orbital period. So there's lots of evidence that this tidal disruption of rocky debris occurs, and we see lots of evidence of these debris disks. And I should emphasize that, yeah, the composition of this can be derived, and we find that these disks are typically comprised of rocky constituents. But the key piece of evidence of planetary debris accretion onto white dwarfs is in the form of absorption lines associated with metals. So here you're seeing a magnesium line in the optical, and we know that the presence of this magnesium line, it has to mean that this material has been recently accreted, because this stuff likes to sink on relatively short time scales. That's just the characteristic frequencies with which we detect these characteristics. But all of this evidence is only indirect evidence of ongoing accretion. And this is where the X-rays come into play, because X-rays give us the real smoking gun signature of active accretion. But more importantly, they can give us an independent constraint on the accretion rate. So there are now a sample of 1,700 metal-polluted white dwarfs. And you can take the abundances and work back a few things. You can derive an accretion rate based on how quickly your models say that your metals sink out of the atmosphere, which is this property here, this settling time. So if you couple a measured abundance, something happened, a metal abundance with a sinking time, we can derive an accretion, an inferred accretion rate of metals moving through the atmosphere. But X-rays can give us a really independent constraint of the instantaneous accretion rate. Because there is there's some large uncertainties about the physics in this settling time. One key uncertainty here is the treatment of convection. Most metal-polluted white dwarfs are convective. Once white dwarfs reach about 20,000 Kelvin and cooler, they become convective. And these convection zones grow monotonically in mass with age. And so initially, you have a very small superficial surface convection zone, but eventually the surface convection zone might contain 10 to the -6 of the stellar mass. And so this convection zone can serve to suspend metals at the surface for much longer time scales. And so we have to accurately characterize where does the convective mixing stop as a function of depth. And there's a few ways you can do this, but 1D models produce a huge discontinuity in the characteristic velocities of these metals. Convective velocities will be on the order of kilometers per second, whereas the microscopic diffusion velocities are on the order of millimeters per second. What's the origin of this discontinuity is the use of a 1D convection model. So we have to go to multiple dimensions in order to really resolve properly the hydrodynamic flows. So I do this with 3D radiation hydrodynamics using the code cobalt. Here you're just seeing a depiction of the difference between a 1D and a 3D. This is a slide through a 3D model. In 1D mixing length theory, you only have convective motion where you satisfy the Schwarzschild criterion for convective instability. Whereas in multiple dimensions, we don't have to make such a crude assumption. This is a emergent intensity of one of my white dwarf simulations. And you can see we have this granular convection. This is just for comparison. This is a solar observation. This is just to qualitatively show that we have granular convection similar to that we see in the sun. But I will just point out that the length scales here are very different. In the solar case, we have megameters, and in the white dwarf case, we have kilometers. But I'm mostly interested in the vertical properties of this convection zone. So here we have 2D slices through 3D simulation boxes. From left to right, we're cooling. So the white dwarf is aging from left to right. You can think of these as like snapshots at specific ages. The blue arrows are indicating the direction and magnitude of the local hydrodynamic, or the local velocity in the X and Z dimensions. The Schwarzschild boundary is indicated by the pink line. So in 1D mixing length theory, you only have a convection zone above the pink line. And you can see already that in 3D, we have significant mixing below this region in the formerly radiatively stable layers. And this is coming from a phenomena called convective overshoot, where parcels of fluid are accelerated within the Schwarzschild, above the Schwarzschild boundary. So where we have convective instabilities being born, but then they have sufficient momentum that they will penetrate beyond the convectively unstable layers, and still they don't contribute very much convective energy flux down there, but they're still contributing huge amounts of mixing. So to study this mixing, I use passive scalars to trace the evolution of trace elements within this overshoot region. And from that can characterize an effective diffusion coefficient, which can then be implemented into a 1D white dwarf structure. And all of that gets us an updated, more accurate characterization of the convective zone mass, or the effective mixed mass, and the diffusion timescale for each element. So here you're seeing this green slab, which starts as a flat slab, and this is evolving in real stellar time. So this is evolving in real time. And you can see that on very short time scales, we're mixing significant amounts of material. You can actually see in these cases that the overshoot region itself is actually larger than the convectively unstable layers. So this is a very pronounced effect, and one that we must take into account. So it produces a prediction of a much larger mixed mass at the surface. It also predicts longer diffusion timescales. A crude accretion rate can be derived from these optical abundances by coupling an abundance with a convection zone mass and a diffusion timescale. So the increase in mass and increase in timescale somewhat cancel out, but not completely. So we do predict an increase in the accretion rate for most metal-polluted white dwarfs. So you're seeing here in black, these are hydrogen atmosphere white dwarfs that have very thin convection zones. The ones up here, the warmer ones don't have a convection zone. Convection hasn't started here yet. The green line indicates the increase in accretion rates when we take into account convective overshoots. All of these black points will also have an increase, but there is a huge computational limitation, which I have a few ways in which I'm trying to overcome, but we need to push to cooler our models to cooler temperatures. But so most of the sample will have systematically underestimated accretion rates using traditional 1D models. And there's other physics that one might want to consider, such as thermohaline mixing, which has been predicted to produce much, much larger accretion rates. Here, the work of Evan Bauer shows that predicts that accretion rates may be as much as 4 orders of magnitude under-predicted. So this is why we need an independent constraint on the accretion rate. And this is where X-rays come in. So to infer an accretion rate from the optical, we have to couple a measured abundance with highly model-dependent properties like convection zone mass and diffusion timescale. If in theory you could measure an X-ray flux, you could adopt a simple model for the X-ray accretion rate, or the accretion rate measured through X-rays, which would take a measured X-ray flux or from that luminosity, and then simply take the white dwarf radius and mass. And those are properties that are much more reliable, well, much more easy to get, let's say, than the, or less model dependent is what I mean there. So that's why we want to be able to measure these systems in the X-ray. In 2020, I had a Chandra observation of 100 kiloseconds and measured for the first time soft X-ray emit. Well, for the first time, we detected X-rays from a metal-polluted white dwarf. Within 100 kiloseconds, we had 5 counts. They were all very soft, but that was enough to confirm this as a source at 5 sigma. Here on the left, you're seeing the ACES counts image. In the middle, you're seeing it convolve with the instrumental PSF. And on the right, you see a Pan-STARRS I band image. Now, this observation was attempted by XMM 20 years before my observation, but you can see that there's a much brighter source near our target within 10 arc seconds, and it was not possible to tease out a detection from the XMM data. And so here, we absolutely needed the angular resolution of Chandra in order to make this discovery. So this is one thing where I'm extremely excited about Access, because we're going to be able to do exactly this kind of thing. Access would be absolutely perfect for studying this system and many others. On the right, you can see the Pan-STARRS I band image, and the difference between the pink and the green is the proper motion. This is a fairly nearby white dwarf, so you're seeing the effect of proper motion there. So from our 5 counts we measured, they were all very soft, which tells us a lot, because the ACES soft sensitivity has decreased significantly. And so we didn't measure, all of our photons were 1.3 kilo electron volts or softer, which is not in the region of the Chandra's effective area where it's most sensitive. So this tells us that this really is a very soft source of X-rays, which was a great discovery, because we had no idea what the X-ray spectrum should look like from these systems. We measure an X-ray flux of 10 to the minus 15 and an X-ray luminosity of 7 times 10 to the 25 ergs per second. And we fit this with a single temperature, optically thin plasma model from APEC, and we find a 0.5 kilo electron volt plasma temperature. Interestingly, this temperature was predicted by Kuipers and Pringle in their bombardment solution. So we think that this is the first evidence of this bombardment solution. So in many accreting white dwarfs, we have a strong standoff shock, which produces harder X-rays. Here, what we think is happening is that the material is at such a low accretion rate that this material is not forming a standoff shock, but instead the material is directly impacting the atmosphere, depositing its energy and emitting X-rays from this locally heated material in the atmosphere. So from that, we can measure an X-ray accretion rate of 10 to the 9 grams per second. I think this is the lowest accretion rate measured in X-rays outside, well, maybe ever, certainly outside of the solar system. But I would love to be corrected on that if that's not the case. And we can compare this X-ray accretion rate to our optical accretion rates. And we find that actually things are extremely consistent. So you see here the pink and the green lines are both optically inferred accretion rates, one using overshoot, the other not. But given that this is a different wavelength, completely different physics, the fact that these agree within an order of magnitude for us was extremely exciting. It actually says that things are going pretty well in the optical. But we do find that the X-ray accretion rate does favor the model with enhanced mixing. So this is really where X-rays are going to be so powerful, already proving to be very powerful as an independent way that we can constrain white dwarf atmospheric models, which can be very difficult to constrain. So this is extremely exciting. I think Axis is going to be very powerful here. One of the key uncertainties here, though, is an upper limit on the accretion rate because we don't have any way to constrain the extreme ultraviolet flux. And so, yeah, there's a few ways that we're going to try and overcome that. One is doing a differential emission measure, so combining the Chandra observation with HST observations. That's an ongoing project, which I won't go into here. I mentioned this XMM observation of the same system. This was 15 years prior. With the knowledge that we've measured a very soft spectrum in Chandra, these authors last year were in fact able to retrospectively tease out a detection from the XMM data. Here they made a 3-color image where the green focuses specifically on the ion lines at 0.7 to 0.8 kilo electron volts. It's easy to look at this and think, how did we not tease out a detection before? But I think having the knowledge that the spectrum was so soft was really what enabled the choice of such a narrow image here. And I'm also working on doing a joint modeling of both of these data sets that you're seeing here. I also have a 500 kilosecond Chandra multi-cycle program with HRC to monitor this system. HRC's soft sensitivity will mean that we have a much better handle on the flux, but we'll be able to look for variability in the accretion rate, which so far we have 0 constraints on. So that would be, I'm very excited about those observations. And where does Axis, what does the future look like with Axis? I think it looks extremely exciting. You're seeing here the X-ray flux that we measured with Chandra. And all of these points here are hydrogen atmosphere metal-polluted white dwarfs. So these are the ones that we're pretty sure are actively accreting. And this is the predicted X-ray flux based on the optical abundances. So you can see that actually XMM is well suited to characterize a fairly large sample of these systems. That's some ongoing work that I'm involved in or that I'm leading. But you can see Axis is going to be amazing for these systems. We're going to be able to detect tons of these things. And I think this is very exciting. I've kind of run out of time, so I'll just quickly say that I'm also leading a cross-match project where I'm looking for serendipitous detections of planet debris accreting white dwarfs. There's one such system in XMM, which I don't really have time to go into. But it has variable optical emission lines, and we're very excited about this system. And recently, actually just this week, one of the cross matches in the Chandra source catalog, which was discovered in an off-axis detection, turns out to be metal-polluted. It has a huge infrared excess. We're very excited about this system. But I just wanted to point out that the big uncertainty here is the 6.5 arc-second PSF for this off-axis Chandra detection. And this is where Axis is going to be so cool, because we're going to find, I think, many serendipitous sources off-axis because the PSF is going to be so good out to such large off-axis angles. So I'm very excited about Axis. That's the punchline. And thanks so much for having me today. I really appreciate the opportunity to talk to you all, and congratulations once again on the amazing news. Thank you.
Great. Rick, did you want to ask a question?
Yeah, you had 5 Chandra photons and you could get spectral information. How'd you do that?
So, I mean, we have, it's being a bit slow to go back. You can see our fit here. I mean, yeah, obviously we would like more photons. We get the spectral information that this thing is very soft. That already gives you a pretty strong constraint. But yeah, we fit our 5 photons. We bin our 5 photons into a spectrum, and we fit with X spec. Yeah, obviously we would definitely like more photons, and specifically for this system, Axis is going to be absolutely incredible. We're going to be able to actually measure lines in this system. And these X-rays here are being produced because we have, magnesium, iron, silicon. We know that these things are in the disk. We know these things are in the atmosphere. So we know that this stuff is very metal rich. And so Axis is really going to allow us to have a much, much better spectrum. And it will probably necessitate updated APEC models, for instance, that can really handle extremely metal rich accreted material, which is not something that's typically needed to model. So yeah.
Thank you.
Yeah, thanks for the question.
Great. Margarita, you want to ask a question?
I'm just trying to unmute. Can you combine it with the XMM now that XMM has detected it having the Chandra knowledge?
Yeah, so that I mentioned very quick.
Spectrum.
I'm currently working on a joint fit of these two. And I also have the HRC data coming in as well. So the idea will be to do a joint fit where we fit one source spectrum, but simultaneously across, because the super cool thing here is that not only do we get the spectrum, the 5 photon spectrum of our source, but we have a very good spectrum of this thing. We don't actually know what this is. It's probably an extragalactic source. But we have a good spectrum now of this thing. And so we can fit both of these spectra simultaneously with the XMM data. And I think this is going to be very powerful. So yeah, if you don't believe my 5 photons as a detection, there are 13 photons here in the XMM data. So we do have more photons, and obviously the XMM soft sensitivity, which I pointed out here. Oh no, I didn't include the plot, but the soft sensitivity, as we know, of XMM is much, much better. And so yeah, I think a joint fit of this data should reveal something pretty will give us better constraints on the spectral characteristics.
That's great. Then you have it separated in Chandra, and I would assume what I see in XMM is polluted by the AGN or whatever it is.
That's it. So
Chandra will allow to see how much when you compare the PSF's pollution.
Exactly. Yeah. So I think it's yeah, it was not possible to deblend these sources. I mean, it's easy to look at this and think,
Right.
how did you not deblend them? But because it's always dangerous, right, to say, okay, well, I take a 0.1 kilo electron volt channel, because you don't know if you're focusing on noise or not. So it's easy in retrospect to kind of think, why didn't we do that sooner? I'm obviously glad that it wasn't done sooner, but yeah, Chandra is super powerful here, and Axis is going to be absolutely amazing for this system and for many others. So I'm very excited about it.
Thanks. Yep.